In this video we will be discussing simultaneous equations with regards to a particular example which I have called example 1. 5 runners have been individually analysed and given a handicap prior to running a 100-metre race. The handicap has been given to ensure the athletes cross the finish line at approximately the same time. The first 50 metres of the race has been graphed below. This graph has not or does not really need to be created, as it says in the question. It's actually provided. And what we have on the x-axis is our time component, on the y-axis our distance, and I can actually put that in there, x and y, if I would like, or if you'd like to make it a little bit more explicit. We're also given a list of coordinates for each runner, runner A, B, C, D and E. We're actually given 2 coordinates for each runner, and that's quite important because we need 2 coordinates in order to establish an equation or a function which will model each runner for the duration of the 100-metre leg. So using the coordinates provided for each runner, determine a linear function modelling the run for each person. Once a function has been found modelling each runner, determine. Question A, what runner will cross the finish line first? And question B, at what distance and time will runner A be overtaken by runner D? Now we need to support both answers with mathematics. There is actually a part C, but it is going to be shown further in this video. Question C is actually asking, or going to ask, who is actually the fastest runner? So out of runner A, B, C, D, E, who is actually the fastest? So we'll get there later. Over the page. So what we essentially have to do is model a linear equation for each runner. Now I've broken my page up into 2, so you can see I've got runner A and runner C. But what I'm actually firstly going to do is start with runner A. So I'll cover up the right hand side and I'll find myself another piece of paper or something thereabouts. To cover up the rest. So what I've done is firstly write the runner's name, or the labelled what runner I'm going to deal with. Firstly runner A, and I'm going to go runner A, B, C, D. I've defined the general form for a linear function, y equals mx plus c, and I've labelled it equation 1. I then need to find the gradient m, and I've written the formula for gradient, which is y2 take y1 divided by x2 take x1, also known as rise over run. I then took the coordinates which were on the previous page for runner A, and I will flip back quickly to show you those coordinates again. Runner A's coordinates 0, 35 and 4 and 50. So I substitute those values into x1, x2, y1, y2, and I simplify to get this fraction of 15 on 4. I'll then substitute that gradient slope m value of 15 divided by 4 into equation 1, which was my general form for a straight line, and called it equation 2. I then need to find c, and to do that I'm going to substitute the first coordinate 0, 35 into equation 2, this one which I've just written, to find that value c, the y-intercept. That's my substitution, substituting 0 in for x and 35 in for y. And when I solve that, or solve for c, I get an answer of 35, or positive 35, and substituting that value back into equation 2 will give me my linear function for runner A. So that's the first one done, and it's a bit of work, but it's not extremely difficult. It's just a bit of more or less just plugging away at the formulas, substituting values, and solving a gradient and a y-intercept value what you then need to do is go through and essentially do this for the rest of the runners. So for runner B, runner C, runner D, runner E. And I'm going to quickly go through that just in case you may be interested. If not, just fast forward the video. Runner B is the next one. So first step, write our formula, equation 1. I then need to find M, and I denote the formula for M is equal to the rise over the run, substituting those values, which were from the coordinates for runner B over the previous page, these two coordinates, 0, 20, and 4 and 50, like so, simplifying and solving before substituting that value into equation 1 to give me equation 2. I then need to find C by substituting one of the coordinates on the other page into equation 2, which I have here, to find that y-intercept. There's my substitution, and finally solving for C before substituting it back into the equation 2 to get my function for runner B. Alright, so there's 2 done. I've got to now do runner C, back up to the top. Y equals mx plus c. Once again, equation 1, I have to find m, the gradient, which is equal to the rise over the run. Substituting the values, or the coordinates for c, into our equation for gradient gives us this. Simplifying and then substituting it back into equation 1. Up here, m8, we get equation 2. I then need to find C, and to do that I need to substitute one of those coordinates. I'll pick the first one into equation 2, which I've just written, to find that value for the y-intercept we call C. There's the substitution, there's my solution for C before substituting C back into equation 2, which is up here, to get my functional model for runner C. Number 4, runner D. Equation 1, linear function, equation for our gradient, rise over run, substituting the coordinates for runner D, which we have here, into our equation for the gradient, gives us this before simplifying and then substituting it back into equation 1 to give us equation 2. We then need to find C by substituting one of those coordinates for runner D into equation 2, I should say, not equation 1, into equation 2 to find our y-intercept. There's the substitution, there's our solution for C before substituting it back into equation 2 up here to get our linear function for our runner D. Okay, we got one more to go. Nearly there. It's a bit of a slow process, but the more you do it, the better you get at it. Last but not least, runner E. We write equation 1, our general form for a straight line, and define our gradient or formula for gradient, rise over the run, before substituting, put back 2 pages now, the coordinates for runner E into that equation, simplifying and then substituting it back into equation 1 up here to give us equation 2, which we then need to find C by substituting one of those coordinates back into 2. There's the substitution for C, there's the solution. We then need to finally substitute that value of C, which is 0, back into equation 2, which we don't actually have to write a C value, we just get left with this here. So there's our 5 functions for our runners. The first question was asking what runner will cross the finish line first. Now once we got these functions, we can pretty much do what we want, and we'll probably be able to answer most questions that are asked. So that's why I've gone and found those functions first. Now what I'm then going to do to answer this particular question is I'm going to substitute the finish line into all of the equations. Now what that means is the finish line in the graph is represented by a y value of 100 because it's a 100 meter race. So this y value of 100 up here I can substitute into each runner's function to get the time in which it took them to cross the finish line. And obviously the person who crossed the finish line in the shortest amount of time will be the person who crosses the line first. So that's what we're going to do. And that's what I've noted. Runners will cross the finish line when y equals 100. So sub y equals 100 into each function to give the time in seconds at which they finished. So for runner A, I went and did that. I rewrote the function for runner A right here, and then substituted the value of 100 into y. And then I'm simply going to solve for x. So to solve for x, I need to get the positive 35 to the other side, make it a negative 35. So negative 35 combined with a positive 100 gives us 65, leaving just the 15 on 4x. I then get the 15 on 4 to the other side by switching the numerator and denominator and multiplying. Alternatively, I could divide 65 by 15 on 4. It will give me the same answer of 17.33 seconds. So that's runner A. Runner B, I rewrote the function, substituted the 100 into the y value, and then solved for x, like so, to get 10.67 seconds. Now, straight up, I can tell runner B is faster than, or not necessarily faster, I should not say that, but runner B beat runner A. Over the page, I have to do runner C and runner D. So we have runner C first. And let's just go runner C and D at the same time. So I rewrote their formulas, or the functions that modelled their particular legs in the race, substituted y of 100 into both functions, and then started solving for x for both functions. And once again, looking at these two, I can see that runner C beat runner D. And the final one, runner E, this is the easiest substitution. It's the smallest function. Substitution, solution, 12 seconds. So I've now got all of the numbers, or all the times in which I need to compare to determine who is going to cross the line first. And of these, 11.25, which is runner C, is the quickest or shortest amount of time, I should say. But back over the page, you might remember runner B had a time of 10.67, which is the fastest of all of them, which I've then stated explicitly. Therefore, runner B, having the shortest time of 10.67 seconds, will cross the finish line and win the race. I then made a note in brackets, because it sort of hit me afterwards, is you're really only assuming, or you can only suggest this is the case if you're assuming that all the runners maintain their speed until the end of the race, which basically means they're not accelerating or decelerating, they're just running at a constant speed for the entire 100 metres. It's an important thing to suggest, it's good communication. The second question, at what distance and time will runner A be overtaken by runner D, is where we're going to have to use simultaneous solutions to answer. Simultaneous solutions, first thing I think of is intersecting linear functions. So runner A and runner D, when I read that question, tells me that there's going to be an intersection between runner A, the green, and runner D, the blue, at some point in time. And you can see runner A and runner D are actually converging towards each other as we progress throughout the duration of the race. So those two are going to intersect somewhere up here. We could extend these lines to figure out where, but and just think for a second that this runner A's gradient was a little bit steeper, they might not actually intersect each other until well and truly off the graph, and it might not be realistic to extend their lines because you might need a lot of paper in that direction to find out where they actually intersect. So we're going to do this algebraically, and to do that is essentially what we call solving using simultaneous equations or solutions. So to do our simultaneous solution, we need to firstly identify the two linear functions for A and D, runner A and D that is. which I've written below each runner. Now, we need to think, and I always like thinking and looking back at the graph, when these two lines intersect, they're actually going to be the same or equal to each other. So we need to let the two functions, the functions for A and function for D, equal each other. And that will be the point at which they intersect. So what I've done here is I've shown that, well, y is equal to y. Therefore, these things here must also be equal to each other. So what I'm going to simply do is let these equal each other and then solve for the x. And that will give me the intersection point, or the x-axis intersection point. I can then substitute a value in to solve for the y-axis intersection point, but the most important step is just getting one of them. Once you've got one of them, you can get the other one by simple substitution. So solve using simultaneous equations. And what I've done there is let both equations for runner A and D equal each other. Here's runner A, here's runner D. It's then just an algebraic manipulation and moving things left and right of the equal sign to isolate your x value, which is what I've gone about doing. I moved the positive 5 to the other side, made it a negative 5 to get my 30. I then moved the 15 on 4x to the other side and made it a negative. Simplified. And over the page, that answer, x equals 16. So the x-intercept, the x-axis intercept for runner A and D on the graph, if I spin that and go back to my graph, right here, I know that at this point 16, if I go up somewhere along this line here, where x equals 16, runners A and runner D are going to intercept. Well, not intercept, but they're going to be, one is going to overtake the other. And because runner D is running faster than runner D is the person who's going to overtake runner A. And that's going to occur, as I said, at 16 seconds. And I rewrote that explicitly, therefore 16 seconds after starting the race, runner D will overtake runner A. Now, to determine the distance at which this will occur from the starting line, we need to substitute that value of 16, x equals 16, into one of the functions for runner A or runner D. And that will give me the y value for the intersection point, which is where the overtaking occurs. So I just chose runner A, function for runner A, called it equation 1, and said substitute x equals 16 into it to get this value y, which represents the distance from the starting line. There's my substitution. Put my 16, x equals 16, into equation 1, before simplifying and solving and getting a value of 95 meters. Now that means that runner means that runner D here, this guy, the guy in blue, runner D is going to overtake runner A 95 meters after starting the race, or runner A will be overtaken by runner D after 16 seconds and 95 meters from the starting line. I'll then put in brackets 5 meters before the finish line, because if it's a 100 meter race, they're going to be closer to the finish line, so I just put that in there just as a little bit of added information, I should say. This is question C, which I didn't actually specify right at the start of the video, but I did mention it was going to appear later in this video, and here it is. Who is the fastest runner? Justify your answer. I threw this one in just to see if it might confuse some people, because a lot of people just initially think, well, the fastest runner is obviously the person who won. But you need to remember that this race is not all started from the same point. Each runner's been given a handicap, which means that they're not all necessarily or the fastest person might not necessarily win the race. So what I have gone and written in a paragraph to answer this question: although runner B won the race, runner E was actually the fastest runner. Should runner B and runner E both have started from the same point, runner E would have won. I'm going to explain this with a couple of numbers, and this is a really important thing to know. Now, this is because speed is a rate of change. Now, the rate of change for speed is distance per time unit, or meters per second in this question. And the rate of change is indicated by slope or gradient on the m value. If you're not aware of it, if we go back to all of these functions which we determined, so here's one. We've got an m value here for this runner. We've got an m value here for this runner, and for these two runners. What those m values are actually the rates of change, meaning the velocity or the speed of each runner in meters per second. And that's really important, and a really important thing to know for linear functions is the m value will always represent a rate of change. This is just representing a constant. So if we go back to the question, here's our rate of change in y equals mx plus c. The m value is our rate of change. And as I said, the rate of change for distance and time is speed. So that's the speed in each of the functions. These are the numbers that support what I'm saying. What I've said is these are all of the m values for each runner. There's 5 values, there's 5 runners. And what I've done is I've listed them from the biggest value through to the smallest value. Now, if you're confused how I figured out what one's bigger than what, I just converted them all to decimals. I simply said 25 divided by 3. And I noted that it was actually bigger than 8. 15 divided by 2, 7.5. So 7.5 is less than 8. So on and so forth. You can go and figure these out in decimal form if you want. I then went and wrote the runners underneath each of the m values. And I noted that runner E had the biggest m value, which, as I said, the m value in this question, or in any question regarding linear functions, the rate of change is represented by the m value. So here's our m value for runner E, which means that he ran the fastest. Did runner E win the race? No. And the reason why runner E didn't win the race is because he was handicapped. A lot more significantly, he actually started at point 0 compared to runner B, who won the race, who got a 20-meter head start on runner E. Now, the reason why runner E started at 0 is because of the fact that he is actually the fastest. Because he's the fastest, he didn't need to be handicapped, or he needed the biggest handicap, I should say. So that's why the fastest person in this instance is not necessarily the person that's won the race.